And I just start with a small advertisement. I forgot to give a reference yesterday. So there is an original paper by Skorbogatov and myself. So in Compositio in 2002. Or everything is also explained in Skorbogatov's book. So the title of his book is Torsors and Rational Points. So you will find everything about descent in this book. So I recall some notation. So from now on, K is a number field. And omega K is the set of all places of K. And recall that gamma is the absolute Galois group. And Kv, the completion of K at V. And yesterday I considered G over K a linear algebraic group, not necessarily connected. And the situation I wanted to consider was y over x, a torsor under G. So if you prefer a principal homogeneous space. So recall that this just means that there is an action of G on Y compatible with this morphism. And the action should be simply transitive in the geometric fibers. This means that if you take a k-bar points on X and you look at the k-bar points on Y over this k-bar point on X, if you take two such points, there is one and only one element in G of k-bar sending one point to the other one. But for this definition, you have to work over k-bar because, for example, it is possible that X has no rational point at all. So I call this morphism F. So F goes from Y to X. This is the torsor morphism. And then I had defined yesterday a special set. So I define the set x of ak to the power f. So the f here refers to the f here. So it is a subset of the set x of ak. And recall that x of ak is just the set of adelic points on X. So X is a variety, and the simplest case is when X is projective, or proper if you prefer. So if X is projective, this set of adelic points is just the product of the local points, x of kv, running over all completions. So I have a certain subset. I recall a definition. X of ak to the power f is defined as the set of adelic points pv such that if you take the evaluation y of PV. So recall that when you have such a torsor, you can take its class y in the cohomology set H1 of xg. And you can take the evaluation. So this is an element in the product of all Galois cohomology set H1 of kvg. And what you demand is that this family of cohomology classes comes from one global class. So this has to be an element in the image of H1 of Kg goes to the product for all V of H1 KVG. Okay, and recall that there is another description of this set using the twisted torsors. X of AK to the power F consists of the union running over all cohomology class C in the Galois cohomology set H1 of Kg of the image of the set of adelic points on each twisted torsor. So there is the notion of twisted torsor, Fc for C, a cocycle, Fc from Yc to X, some twisted forms of the original torsor Y. And then for each of these twisted torsors, you look at the set of adelic points, you take the projection, and you obtain this set as the union of this projection. So this is the so-called Selmer set, some equivalent of the Selmer group. And we had seen that the set of rational points x of k is a subset of this set x of ak to the power f. This is just a consequence of the functorial properties of non-abelian, étale, and Galois cohomology. And actually, we can say more. So this is a very simple observation. But there is a more specific result about the closure of x of k in this set x of ak. So defined. So here I assume that x is projective. So define over line x of k as the closure of x of k in this adelic space, so for the product of the V-adic topologies. Then you have the following theorem that you can find, for example, in our paper or in Skorobogatov's book. Actually, not only x of k, but the closure of x of k is a subset of this special set x of ak to the power f. So for any torsor f from y to x under any group G, so I'm not going to give the proof, but for example, if G is connected, this is an easy consequence of the well-known Borel-Serre's finiteness theorem in Galois cohomology. And for G not connected, it's an extension of Borel-Serre's theorem. So this statement is classical in the case of descent under a group of multiplicative type, for example. So in particular, this means that we get an obstruction so not only to the existence of a rational point, if this set is empty, but also to weak approximation. Because if you take an element in the adelic space that is not in this set x of ak to the power f, it cannot be in the closure of the set of rational points, so it cannot be approximated by a rational point. So this is the so-called descent obstruction associated to the torsor F from Y to X.
I'm sorry, so this X of AK F is closed to secondary.
Yes, it is actually. Yes. So it contains, but the point is that you have to prove it. So to prove it is closed, you have to assume that X is projective. This is important for this statement. Maybe I can give a few more details. The point is that when you describe this set X of AKF as a union of these sets, of the image of the adelic points on the twisted torsors, it is easy to show that each of these is closed. But what you have to show is that this union is actually a finite union, that only for finitely many cohomology classes C, this set is non-empty. So this is the part that uses the finiteness theorem by Borel-Serre. So if you prefer, the theorem maybe should be stated, this is a finite union if X is projective.
So for almost all C, there's no adelic point?
Yes, for almost all C, no adelic point on the twisted torsors. Now, for example, if G is finite, this corresponds to the classical Hermite statement about the fact that there are only finitely many fields unramified outside some fixed set of places. But it's not so easy if you work with a non-connected group, for example. Okay, so this is an obstruction to the existence of a rational point or to weak approximation. And now the question is, compare this obstruction with the classical Brahmanian obstruction. So today I'm not going to give a general answer to this question, but I will give examples. So the first very important case is the case of a group of multiplicative type. And this is essentially the classical statement in a descent theory. So if you take descent theory of Colliot-Hellen and Sansuk, so from now on, I assume that X is projective, by the way. And this theory was refined by Skor-Bogatov because Colliot-Hellen and Sansuk deal with the case of a torus, and this was extended to any group of multiplicative type by Skor-Bogatov. So this theory says that the Brahmanian obstruction essentially is equivalent to all descent obstructions, but associated to groups of multiplicative type. And this statement should be refined. You have to consider the Brahmanian obstruction associated only to a part of the Brauer group, to Brauer 1 of X. And Brauer 1 of X, by definition, is the kernel of Brauer X goes to Brauer X bar. So maybe I should explain this. So Brauer X is the Brauer group of X. X bar is X cross K. K bar. So you consider just a small part of the Brauer group, elements of the Brauer group that are killed if you go to the algebraic closure. Now you consider all Brahmanian obstructions associated to these elements. Then the statement is that this obstruction is equivalent so it is equivalent to considering all descent obstructions for G of multiplicative type. This means that you consider the Brahmanin set associated to this subgroup, the set of adelic points satisfying the Manin conditions, but for elements of this group. And then you consider the intersection of all sets x of ak to the power f, for f a torsor under a group of multiplicative type. The statement is that both sets are the same. So that's the first case, the case of groups of multiplicative type. Using these descent obstructions, you do not refine the Brahmanin obstruction. Basically, if you consider all these descent obstructions, you get the same thing as the Brahmanin obstruction associated to algebraic elements of the Brown group. And now, you can ask what happens if you consider Brahmanin obstructions associated to elements in the whole Brown group, not only algebraic elements like this. So here is the answer. Oh, by the way, I should have said that a group of multiplicative type is a commutative linear algebraic group, which is an extension of a finite abelian group by a torus. So, for example, a finite abelian group or a torus. So the second case is the case when you consider Brahmanin obstruction associated to transcendental elements. So there are examples of Brahmanin obstruction with the transcendental elements of the Brown group. So transcendental means that these are elements that are not in this set. They are not killed if you go to the algebraic closure. So for example, there is a counterexample to weak approximation for K3 surface given by Wittenberg. In 2002. And I had an old example in 1994 for a threefold conic bundle over P2. So these transcendental Brahmanin obstructions do not correspond to classical descent obstructions, that is, to descent obstructions for G of multiplicative type. So this is not part of the descent theory of Kolyotelen and Sansuk, but nevertheless, they correspond to descent obstruction for a very simple group for G equals to PGLN. And here is the explanation. Indeed, you have an exact sequence in étale cohomology. So you use the same exact sequence as yesterday, GLN, PGLN, and the kernel is GM. So if you take the long cohomology exact sequence, it is a central sequence, so you have an H2 term. So it goes like this. H1 of x GLN, H1 of x PGLN, and here you have a combodary map to H2 of x GM, and by definition this is the Brown group of x. So this is one way to relate descent obstruction associated to PGLN to Brahmanin obstruction associated to any element of the Brown group. But here, of course, you have to use a very deep result, and quite recent, actually. So this is a theorem by Gaber. Yes, but the point is that actually in this situation, it is the same as the Azumaya-Brauer group. This is the result by Gaber. And of course, you have to use this result to prove the statement about the relationship with the Brahmanin obstruction. So by a theorem of Gaber, if you take the union for all n of the image of H1x PGLN, so by definition, this is the classical Azumaya-Brauer group. So in this situation, for a smooth projective variety over a field, it is the same as Brauer X. So I should have said this is the cohomological Brauer group. So using this at the corresponding classical result for fields, for a number of fields and local fields, it's not too difficult to see that if you take the descent obstructions corresponding to PGLN, you obtain all Brahmanin obstructions, even the transcendental Brahmanin obstructions. Yes, yes. Now it's important because, for example, if X is not smooth, this group is not necessarily torsion. The projectivity itself for this statement is not important, but it is if you want to define the descent obstruction to weak approximation. Because if the variety is not projective and you want to define an obstruction, you would obtain some kind of obstruction to strong approximation, not to weak approximation, because the topology on the adelic space is not direct product of the adelic topologies if X is not proper. So that's why for this I assume that X is proper. So this means that even for the Brahmanin obstruction, it's interesting to deal with the non-abelian descent obstructions, because just with PGLN, you recover more complicated Brahmanin obstructions, transcendental Brahmanin obstructions. And so finally, now, you can ask the question, what if G is finite and non-abelian? Then the result is that the descent obstruction can be finer than the Brahmanin obstruction, which means that if you take the Brahmanin set, the set of adelic points satisfying all Brahmanin conditions, it is not necessarily a subset of this descent set x of ak to the power f. And an example is, and now we come to the title of today's talk, Bielliptic surfaces. So now I'm going to discuss bielliptic surfaces. So this is the third part in this series of talk. And now we start with some general facts. So first of all, what is a bielliptic surface? So consider x over k. So when I say that x is a bielliptic surface, this means that it is a bielliptic surface over k bar. So what does it mean? over k bar. So if I take x bar, x over k bar, so geometrically, x is an étale quotient of the product of two elliptic curves. So E1 cross E2 modulo a finite group F. So E1 and E2 are elliptic curves. And F is a finite group acting freely. So it's an étale quotient. Actually, there are 7 possibilities for F. So you can find this in any good book about complex surfaces. And by the way, all possibilities are abelian. For surfaces, there are no examples with F non-abelian. So this is what an elliptic surface is. It's one type of surface of Codera dimension 0. I can say a little bit more about the geometry of such a surface. So for example, H1 and H2. So for such a surface, you have H2 of X of the geometric genus is 0. And the dimension of H1 of X OX, so if you prefer the dimension of the Albanese variety, is 1. And something which is very interesting for these surfaces, and that I'm going to use, is the fundamental group, the geometric fundamental group pi 1 of x bar. So this is by definition the, let's say, the étale fundamental group. Well, if you don't like étale fundamental groups, we can just embed K to C, consider X over C, and just consider the usual topological fundamental group. This one is just the profinite completion of the usual topological fundamental group. And the important fact is that pi 1 of x bar is not abelian. This means that there are interesting geometric coverings with a Galois group that is not abelian. This is quite easy to see because if you set y, the product of the two elliptic curves, or let's say y bar maybe, just to recall that it is over k bar, then you have, using just the étale covering y bar goes to x bar with the group F, you have an exact sequence like this. 1 pi 1 of y bar, pi 1 of x bar, and here the group F, finite abelian. So this works just like Galois theory. Imagine that there is a universal covering, then this F is a quotient, this one is a subgroup. But pi 1 of y bar is just pi 1 of the product of two elliptic curves. So this is just z hat, or z if you don't like just étale fundamental group, to the power 2 times the genus, the dimension, I mean, so the power 4. But here, if you consider the abelian part of the pi 1 of x bar, it has rank 2, because it's 2 times the dimension of the Albanese variety. So in particular, pi 1 of x bar cannot be abelian because you have a too big abelian subgroup here. Okay? So these bielliptic surfaces actually have funny arithmetical properties. And these properties were first used by Kolyotelen, Sansuk, and Skorobogatov to disprove a conjecture by Maser. And shortly after, they were used by Skorobogatov to give the first counterexample to the principle, not accounted for by the Brahmanin obstruction. So now I'm going to explain a little bit the construction by Skorobogatov. So to make things simpler, now I'm going to assume that the group F is just Z mod 2. This is one special case of bielliptic surface. So this means that if you prefer, you will have a Y over X like this. So Z mod 2 covering, étal covering. And so X is the quotient of Y by a fixed point free involution. Say tau involution. And over K bar, this Y bar is going to be the product of two elliptic curves. So this is the situation. And Skorobogatov has constructed a special case of this situation when there is a counterexample to the Hasse principle not explained by the Brahmanin obstruction. So I'm going to give a few more details about Skorobogatov's construction. So I'm not going to give the counterexample explicitly, but just explain how it works. So it's section number 4. So first of all, I'm going to state his theorem. So it's in 1997. The paper has appeared in Invenciones in 1999, and a good report is once again Skorobogatov's book. So here is the theorem. There exists a bielliptic surface X over Q, field of rational numbers, such that first of all there is no rational point, X of Q is empty, and there is no Brahmanin obstruction to the existence of a rational point. So I'm going to write this X of AQ to the power BR is not empty. So this is the set of adelic points satisfying the Brahmanin conditions. So I'm going to write this down explicitly. So by definition, yes, sorry. Sure, you just have to wait for 10 more minutes. or if you want, I can give you the result before everybody. If you take an arbitrary bielliptic surface, assume that there is one rational point, then the closure of the set of rational points is strictly smaller than the set x of aq power br of adelic points satisfying the Brownian conditions. That is, it never works for bielliptic surface. It is never true that the Brownian obstruction to weak approximation is the only one. Never. So, but just have to wait. Okay, so I recall just the definition.
Is it only for weak approximation or also for existence of points?
No, for weak approximation. So you assume, take a bielliptic surface. Assume that there is at least one rational point. Okay. Then the conclusion is Brownian obstruction to weak approximation is not the only one.
What is the example for existence of rational points when the Brownian obstruction?
Yes, this is the theorem, this statement. But I just have to give this definition. X of aq to the power of br, it is the set of adelic points satisfying the Brownian conditions. So namely, is the set of adelic points PV such that for all elements alpha in the Brown group, if you take the sum over all places of JV of alpha of PV, so JV is the local invariant from the Brown group of a completion KV to Q mod Z, local invariant in local class field theory. This has to be 0. So the statement by Skor-Bogatov says it is possible that this set is non-empty. There is at least one adelic point satisfying the Brownian conditions, but the set of rational points is empty. No, because I didn't bring them. You can find them in Skor-Bogatov's paper, but I'm just going to explain what the ingredients are. They are not very complicated, actually. So I'm just going to explain the ideas in the construction. So it goes like this. You have this x, this y, which is a product C cross D, and here CD are curves of genus 1, and D has a point. But C has not. And then you have another, so this is a Z mod 2 covering. And you have another covering, Y prime, which is C prime cross D. C prime is another curve of genus 1. And actually, C prime is obtained as a principal homogeneous space of an elliptic curve E. And there is one very specific condition. Its class C prime in the Weierstrass group must be in the Tate-Shafarevich group of E. So you have to start from a curve with non-trivial Tate-Shafarevich group. And it's a more precise condition. It has to be of order 4. And C prime goes to C is an étale covering with group the 2 torsion of the elliptic curve E as a K group, as a group scheme. Okay, so these are the datas. And then basically there are 2 steps in the proof. What? Principal homogeneous space, PHS. I could write torsor instead of principal homogeneous space. Just a twisted form of the elliptic curve E. So there are two steps in the proofs. Two steps. The first one is the most difficult one. You have to prove that under some conditions, and the important condition is that there is no point, no non-trivial point of order 2 in E over Q. You prove that if you look at the image of Breuer X into Breuer Y prime, so I'm going to call this F, and this whole here F prime. So you take the pullback F prime star of Breuer X, so this is a subset of Breuer Y prime. You prove that in some sense this image is not too big because it is a subset of pi star of Breuer D. So what is pi? It's just the second projection, pi from Y prime to D, second projection. So this means that if you consider the image of the Breuer group of this variety into this variety, everything comes from the Breuer group of D. So this is really the difficult part of the proof. It involves very precise computations with Breuer group of X bar, Néron-Sévry group of X bar, and so on. But once this is proven, the point is now it's very easy to construct adelic points in the Breuer-Manin set. Why? So indeed, you just take one adelic point on C prime, because C prime has points everywhere locally. Let's say RV in C prime Q. You take now a global point, a rational point, let's say Q, no, not Q, P in D of Q, because the assumption is that D has a rational point, and then you project just RV P to X. And now by functoriality, it is obvious that these points satisfy the Breuer-Manin conditions, because when you make the computation, sum of JV of alpha of PV, by functoriality, you will just get this sum with the beta of PV for this P here, and for beta, an element of Breuer group of D. But P is a global point, so the sum of all local invariants has to be 0. So the idea is that the image of Breuer X in Breuer Y prime is very small. Everything comes from Breuer D, but since D has a global point, a rational point, it is easy now to verify that this point, this adelic point, so this is an element in Y prime of AK, AQ, that this one is an element of the Breuer-Manin set. So just by functoriality of the Breuer-Manin pairing. So this is the first part of the proof. And the second part is easier. You show that x of q is empty, just using descent from y to x. Because if you recall, if you remember the descent statement yesterday, the set of rational points of x is obtained as projection of a set of rational points on the miscellaneous twisted torsors of y. But on Skor-Bogatov examples, it's easy to check that only two twists have points everywhere locally, y and one other twist. And then you check directly that these two twists don't have a rational point. So this part is really an explicit computation. It's not difficult. The difficult part is the first one, and of course, finding a situation like this with these very drastic conditions. Okay, so I'm not going to say more, but of course, it's a very good idea to read a very beautiful paper by Skor-Bogatov, or his book, if you prefer. Okay, so that's one example. But now we would like to understand where it comes from and what is the obstruction. And it turns out that everything can be explained in terms of the descent obstruction. So in Skor-Bogatov's paper, all was explained in terms of some kind of iterated Brahmanian obstructions, but it's simpler to understand this counterexample by means of the descent obstruction. So generalization. So actually, in Skor-Bogatov's counterexample, so what happens is that you have your x, you have your y, and you have some other z here with a g. So z goes to x is a torsor under a non-abelian finite group. Let's say G. And I can tell you what G is, at least over the algebraic closure. It is just a semi-direct product of the four torsion of the elliptic curve E by Z mod 2. The action here is by -1. So it's not a very complicated group. It's of order 32. And what happens is that in his counterexample, the descent set x of aq to the power g for this g is empty. So what we have is a descent obstruction to the existence of rational points. So it can happen that for a finite group G, this descent set is empty, but the Brahmanian set is not empty. So you have refined the Brahmanian obstruction using descent under a non-abelian finite group. And actually, you can prove a general statement, not about the Hasse principle, because of course it's very difficult to ensure that there is no rational point, but there is some kind of negative statement about weak approximation, and it's related to the fact that the fundamental group, the geometric fundamental group, is not abelian. Because if you want to get interesting torsors like this under a non-abelian finite group, this means that the geometric fundamental group is not abelian. So here is a general theorem. So general result about weak approximation. So this is the following theorem. So in the paper appeared in Annales de l'École Normale in 2000. So let x over k be projective, smooth, geometrically connected, and here, to avoid an empty statement, I have to assume that there is at least one rational point. Now I have to make geometrical assumptions. Assume that, well, let's say bar x bar invariant by Galois is finite. So gamma is the Galois group, and x bar is x over k bar. So for example, this is satisfied if h2 of x or x is 0. Well, probably you could prove this in general if you assume some conjectures by Tate. But anyway, if you have this condition, this is satisfied. And the second very important assumption is that the geometrical fundamental group, pi 1 of x bar, so x bar is x over k bar. Now you assume that this one is not abelian. So this is the second assumption. And you have to add an assumption about the Albanese map. Where the technical condition is faithfully flat with reduced and connected fibers, but essentially this means that the important assumption is that the dimension of x has to be strictly bigger than the dimension of its Albanese variety. I'm going to explain why. Oops. Sorry. So the dimension of h1 of x or x. So these are the assumptions. And then what is the conclusion? Then the closure of the set of rational points is strictly smaller than the set of points satisfying the Brahmanin conditions. That means, if you prefer, Brahmanin obstruction to weak approximation with these assumptions is never the only one. And what are the ideas? Well, the first thing is that you use the assumptions on H1 and H2 to construct many points in the Brahmanin set, this set. And then you use the fact that the geometric fundamental group is not abelian to obtain descent obstructions for these all these descent obstructions related to non-abelian finite group. So for example, well, any bielliptic surface satisfies these assumptions, or more generally, any étale quotient of an abelian variety so this works in higher dimension. And there are also examples with more general elliptic fibrations over P1. But here the condition, so you have elliptic fibrations with H1, you take special fibrations with H1 and H2 0, and the condition for this group being non-abelian is that there should be at least 3 multiple fibers. So the bielliptic surface corresponds to the case when you have 4 double fibers, and you have also examples with surfaces of general type. Actually, you can construct funny examples with surfaces of general type, examples when the Brauer group itself is trivial, but you have a small but non-abelian fundamental group, and so you can apply this theorem. An open question would be to construct such a counterexample, but a counterexample to the Hasse principle using this descent obstruction for such an elliptic fibration, for example, for a proper elliptic surface, or for a surface of general type. I don't know how to do this, but certainly it should be interesting. And so finally, the conclusion is that using abelian groups, you cannot refine the Brownian obstruction. That's the classical theory of descent. Using non-abelian finite group, you can refine this Brownian obstruction. Now the next question is what happens with the more general groups. There is one theorem that if you take a linear connected group, you cannot refine Brownian obstruction. So PGLN was a special case, but if you take any connected linear group, this works the same. You will not get more than the Brownian obstruction. So the next question is what happens if you take a non-connected linear group, but which is an extension of a small finite abelian group by a connected group. So for example, you take an orthogonal group, and what I will explain tomorrow is that once again you can have a refinement of the Brownian obstruction, and this will be the case for Enriquez surfaces. So I will explain this tomorrow. Thank you.